Okay, so let's suppose we have a linear least squares problem. The source might have been a data fitting problem, but it doesn't have to be. There are other sources of these problems as well, and we just solve them in the abstract case now. So the abstract formulation of the problem is that we're given an m by n matrix A, and here we're going to emphasize that m is greater than or equal to n. In other words, it has more rows than columns. It's tall and thin. Okay, we also have an m by 1 vector B, so it has the same height as A. And the goal of the problem is to find an n by 1 vector X. Remember, n is smaller, and it fits the number of columns of A, so it's a shorter vector. Okay, and we want to minimize the difference between those two vectors as measured in the 2 norm. Now, if we thought about the square case where we had AX equals B, right, each line of that equation is one equation, okay, and each entry of X is a variable. Well, we had just as many equations as variables there. But now we have more equations than we have variables, and in fact, we would call this overdetermined. Okay, so in general, when we have more equations than variables, we can't expect this to happen. We can't expect that we get the difference to be exactly 0 anymore. We just try to make it as small as possible. There is, however, a simple characterization of the solution that we can use algorithmically. So there's a theorem that states that provided we can satisfy this condition with x, then if x satisfies that condition, then it's a solution of the linear least squares problem. So the overarching idea of this proof is to say, well, if x truly minimizes this thing that we have here, if x is to minimize this, then any other vector that we put in here has to give us at least as large a result. So if v is any vector whatsoever, I should find that the norm of ax plus v minus b is actually at least as large as the one that we're calling the minimum. If we can prove that, then x really is something that minimizes the norm over all vectors. And so the rest of the proof is just the details of the algebra. And we are going to use the fact that this is in the 2 norm. That turns out to be critical to making this easy to do. So if we take that 2 norm squared, well, the 2 norm squared of any vector is the inner product of that vector with itself. Okay, and now I'm going to rearrange these pieces so that the v part stands on its own. So I'll have ax minus b plus av, and here I have ax minus b plus av. Okay, now I'll multiply these out into 4 terms. So I have ax minus b transpose times ax minus b plus I have av all transposed times ax minus b plus I have ax minus b transpose times av, and then the last term is the av transpose times av. Okay, so let's focus for a minute on the 2 middle terms. So with linear algebra, you always have to be a little bit careful about what it is that you're writing and what it means. So ax minus b is an m by 1 vector, right? So is a times v. V is any n vector, so a times v is an m vector. So what we have is the inner product of m vector with m vector. In other words, it has the form of W transpose Z plus Z transpose W. Right? So W would be AV and Z would be AX minus B. Well, an inner product between two vectors is just a scalar. So it doesn't matter whether I write W transpose Z or Z transpose W, they're the same thing, they're the same scalar. The inner product result doesn't depend on the order of the two vectors. So, with that in mind, okay, the first term is clearly another norm. AX minus B, 2 norms squared. The two middle terms are the same thing. So I'll write 2 AV transpose AX minus B. And then the last term is clearly a norm again. Okay, we're almost there. This is the same thing here. I'm going to rewrite, I'm going to use the fact that the product or the transpose of a product is the product of transposes with the order reversed. Okay, this is left out the same. And now you see the whole point of doing things this way. Given the assumption of the theorem here, okay, this term here is exactly 0. So now what we have, need a little bit more room. What we have comes down to the 2 norm of AX minus B squared plus the 2 norm of AV squared. Well, the norm of anything is always a non-negative number, so that's got to be at least as big as the norm of AX minus B squared. So you scroll back from beginning to end, we have this term squared is greater than or equal to this term squared. Well, that's what I said at the beginning. If we could prove that, then we've actually proven that x is a minimizer. So we're done. Okay. So this condition from the theorem that A transpose times the vector AX minus B is equal to 0, that's actually the same, right? We can just rearrange that by multiplying things out and moving stuff to the other side into A transpose AX is equal to A transpose B. So by associativity, A transpose A, that's n by m times m by n. So A transpose A is an n by n matrix. Okay, X is an n by 1 vector still. And A transpose B is n by m times m by 1. So that's an n by 1 vector. And so what we have is a square linear system for X. And that square linear system, let me write it here again, A transpose AX is equal to A transpose B, is called the normal equations. So if we can solve the normal equations, we can solve the linear least squares problem. And in fact, mathematically, we just take that matrix inverse. So this whole matrix here, which if you work it out must be n by m, often has a special symbol, A plus, or sometimes it's A dagger. It's called the pseudo-inverse of A. Now, that sounds like a pretty simple story. We know all about solving linear systems of equations that are square, and so we could just end the story right there. But the story goes on because this matrix A transpose A actually has two very important properties. One's called symmetry, one's called positive definiteness, and those two properties together make this easier to solve than the average system, and so we're going to have to go into some of the details about that.